Ah, okay, here we go. I lost the PDF for a little bit, but I found it. Okay, here we are.
All right.
So
So
is it up and working?
it's up and working. Yeah. So today we have Fitzpatrick from MIT, live from New York City, I think.
Yep.
All right. And he's going to tell us about kinetically decoupling relic dark matter.
Okay.
So take it away. Are you okay if we interrupt with questions?
Yeah, totally. Yeah, totally fine. Yeah, I mean, yeah, I guess it is close to the limit of a discussion. It can be probably the best, I guess. It's
All right.
kind of
Well,
fun.
take it away.
Okay, cool. Yeah, yeah, thanks a lot, everyone, for the opportunity to come tell you guys about this work. So I'll be describing this kinetically decoupling relic, and really more broadly, what I'll be describing today is new pathways to the relic abundance of vector portal dark matter. And in particular, I'll highlight this kinetically decoupling relic scenario so that we can walk away with kind of one concrete example of one of these new pathways. And so this is from work with Hongwan Liu, Tracy Slatyer, and Yu Dai Sai. So let me start by asking, why is it interesting to think about light thermal dark matter? So there are many suggestions for new physics and new particles that would solve the dark matter puzzle, that might solve the dark matter puzzle. And among these, one important and for a long time now well-studied class has been the weakly interacting massive particles. And so these are a general class of dark matter candidate with masses in the GeV to TeV range, and with weak scale interactions with the standard model. And the WIMPs are the simplest example of a thermal relic. So these are particles that were once in thermal equilibrium with a standard model plasma, and as the universe expands and cools, subsequently freeze out to the constant co-moving density that we observe. And the WIMPs are theoretically attractive because they arise naturally in various beyond standard model theories, most notably in models of supersymmetry. And also because of the observation that the thermal production of WIMPs through these 2-to-2 through their 2-to-2 self-annihilations to the standard model, like through this process that I'm showing at the top here, with a weak scale cross section, naturally gives rise to the observed relic density of the dark matter. And so this is called the WIMP miracle. But now the WIMPs have kind of long been a focus of theoretical investigation, and there's also been increasingly strong experimental constraints being placed on new physics at the weak scale. And so we're also inclined to think about what other alternative thermal production mechanisms might exist for the dark matter. And in particular, current direct detection constraints are most sensitive to dark matter with masses greater than around 10 GeV, and they quickly become insensitive at lower masses. So for example, I'm showing here results from mainly the xenon 1-ton experiment on constraints on the WIMP nucleon scattering cross section as a function of the WIMP mass. And the details of the plot aren't too important. The main thing I want to say with this is that you can see that at masses less than around a GeV, these constraints quickly become very insensitive. And it's also a particularly exciting time to think about light dark matter because there's kind of a growing frontier of new experiments searching for light dark matter and that are becoming available and being planned that will soon explore the parameter space of light dark matter with unprecedented sensitivity. So it's a kind of a particularly exciting time to think about the kinds of models that might populate this sub-GeV region for the dark matter. And so here I'm showing a list of some of the previous light thermal relics that have been studied. And today what I want to do is really carefully explore, an already pretty well studied hidden sector model, the vector portal dark matter model. Yeah, an already really very, very well studied model. But really carefully explore the parameter space of this model, and in doing so find a rich set of new pathways to the relic abundance of vector portal dark matter. And among these new pathways, and these new pathways that can give rise to light dark matter. And among these new pathways, I want to highlight in a bit of detail this kinetically decoupling relic or Kinder scenario, yeah, just so that we can walk away with kind of one concrete example of one of these new pathways. So here's an outline of how I'd like the rest of the talk to go. So I want to start by reviewing some of the previous light thermal relics that have been studied, in particular the SIMP and Elder scenarios. And there's kind of a lesson I want to take from the SIMP and Elder scenarios that I'll state when I review them, that I want to apply to later when we think about this vector portal dark matter model. So then I'll jump into thinking about the vector portal dark matter model, and start by reviewing some of the light thermal relics that have been previously studied in the context of this model, in particular the forbidden and not forbidden dark matter scenarios. And then I'll describe new pathways to the relic abundance of vector portal dark matter. And among these new pathways, I want to describe in a bit of detail this kinetically decoupling relic, or Kinder scenario. I'll do this by outlining the thermal history of a specific realization of Kinder, and then I'll identify the generic kind of region of parameter space in which, in this model in which Kinder lives, and also see where it lies in relation to other new pathways, other new freeze-out mechanisms in this vector portal dark matter model. And then I'll move on to describing the experimental constraints on vector portal dark matter. Okay, so let's start by reviewing some of these previous light thermal relics, and starting with the strongly interacting massive particle, the thermal SIMP scenario. So in the thermal SIMP scenario, it's these 3-to-2 self-annihilations among dark matter particles that determine the relic density of the dark matter. So in this scenario, imagine that at once in the thermal history of the universe, these 3-to-2 self-annihilation processes among dark matter particles is active and maintains chemical equilibrium in the dark sector. And at the same time, this elastic scattering process between dark and standard model particles shown at the right is active and maintains thermal equilibrium between the dark and standard model sectors. And as the universe expands and cools, the dark matter depletes through these 3-to-2 self-annihilations up until the point at which the rate for these 3-to-2 self-annihilations falls below the Hubble expansion rate, and this process freezes out. And this signals the freeze out of the dark matter. And just as a note, I'll usually place a box like this over a process when I'm indicating that process has frozen out kind of throughout the talk. But so now we can solve this freeze out condition by dimensional analysis. This 3-to-2 thermal average cross section scales this way with the dark sector coupling in mass, and because freeze out happens during the radiation dominated era, the Hubble rate scales like temperature squared. So we can solve this freeze out condition for this relation among the dark matter mass and coupling, which when we match to the observed relic abundance of the dark matter, naturally leads to dark matter with a mass of around 100 MeV and with strong coupling. And so this natural emergence of the strong scale in this thermal SIMP scenario is kind of an attractive feature of this framework, and is kind of, yeah, it's called the SIMP Miracle as an analogy with the WIMP miracle. Okay, so now let's
quickly. There's a question in the chat.
Oh, I see.
Is there any reason why the dark sector equilibrium is maintained by a 3-to-2 process and not, say, 2-to-2? I guess, well, how do we understand that 3-to-2 process is the dominant one?
Yeah, I guess I haven't said anything about the kind of model that you would rely on to do this.
Yeah.
Yeah, I guess everything I've said so far is kind of more model independent, and so it's more from the point of view of like, realizing a scenario where it is this 3-to-2 process in order to get light dark matter this way.
Okay.
I don't. Yeah, I have to confess that I don't have a clear memory of some of the model building that happens after to realize this scenario.
So it's just for this scenario then that you need the 3-to-2?
Sorry, what was that?
It's to realize you need the 3-to-2 to realize this particular scenario.
Yeah, I think what the 3-to-2 gives you is like a particular, yeah, it's like because of the way the cross section of the process scales in the freeze out calculation, you get it gives you light dark matter. So for example, if you did like a 4-to-2 process, if you were able to realize that, you would get like even lighter dark matter.
Okay, yeah, that makes sense.
Yeah, I have to, I would have to, I don't have a sharp model. I don't have like a concrete model in mind at the moment of how this was done, but there's a few after the original, I think, yeah, in the original SIMP paper, there's a model that they write to do this, and then there's kind of future models that realize this in various ways, but this is kind of just a general idea.
But is one of the points that if the 3-to-2 process is allowed and it's relevant, or it's happening commonly enough because this is a strongly interacting theory, then this does change the abundance of these particles as they sort of fall out of equilibrium? Or is it just that they're maintaining equilibrium through this 3-to-2 process?
I guess I might not be totally understanding the question, but
yeah. So is the 3-to-2 process actually changing what I would think was the final abundance in the SIMP case? That's basically all I'm asking.
Yeah, yeah, I mean, it's the 3-to-2 process that determines the relic abundance.
Right. Yeah. That's all.
Does that answer your question?
That was my question. Yeah.
Oh, I see.
That's really...
So I think it just determines the relic abundance in the end. Once the universe freezes out, you have less dark matter particles. So you have like a lot of them, and then they just you're just depleting that large number, and then in the end you have a smaller amount that is there. So you're right. You're just depleting that number density.
Yeah, I think that's right. Yeah, I think that's right. Yeah, and it's the, yeah. So that's the idea here. It's the freeze out is through the 3-to-2 process, which determines the relic density. Okay, cool. Okay, so now I want to move on to thinking about this elder scenario. And so, right, so this elastically decoupling relic. So in both the WIMP and SIMP scenarios, it's number changing processes, it's dark matter number changing processes that determine the relic density of the dark matter. But remarkably, it's also possible to realize a scenario in which this elastic scattering process, rather than number changing processes, determines the relic density of the dark matter. And so that's this elder scenario. So in this elder scenario, imagine that at once in the thermal history of the universe, this elastic scattering process is active and maintains thermal equilibrium between the dark and standard model sectors. And at the same time, this 3-to-2 self-annihilation process is active and maintains chemical equilibrium in the dark sector. And so far, this is the same as in the thermal SIMP scenario. Except in this case, as the universe expands and cools, the first process to decouple is this elastic scattering process. And this happens when the rate at which the elastic scattering process transfers energy between the dark and standard model sectors can no longer compete with the rate at which these 3-to-2 self-annihilations convert mass to kinetic energy in the dark sector. And so when this happens, the two sectors elastically decouple. They're now thermally secluded from each other, and the dark sector evolves with its own separate temperature T prime, which is different from the standard model temperature T. And elastic decoupling happens while the 3-to-2 self-annihilations are still active, and in particular, they're still actively converting mass to kinetic energy in the dark sector, which is now thermally secluded, so they're heating the dark sector up in a process called cannibalization, which I'll describe in the next slide. But the important thing to see about cannibalization here is that during this period, the dark matter evolves, because it's being heated up, the dark matter evolves with a nearly constant temperature and likewise nearly constant co-moving density. And since it evolves with a nearly constant co-moving density during cannibalization, when finally the 3-to-2 process freezes out, and this signals the freeze out of the dark matter, the relic abundance is nevertheless determined by the elastic decoupling process. And so let's examine it in a bit more detail, this cannibalization scenario, to better understand how it leads to this elder scenario, and also because cannibalization is something that'll turn up again when I talk about this Kinder mechanism. in the context of the dark photon model. Or yeah, in the context of vector portal dark matter. So again, cannibalization occurs after kinetic decoupling, during which the two sectors are thermally secluded, and so it can no longer transfer entropy between each other, and the dark sector evolves with a constant co-moving entropy density. And at the same time, the still active 3-2 self-annihilations maintain chemical equilibrium in the dark sector and at zero chemical potential. And both of these facts can be used to determine the relation between the dark sector temperature T prime and the standard model temperature T. You find that T prime scales logarithmically with the standard model temperature and is mostly fixed by its value at kinetic decoupling, TD. And so this quantifies the statement that the dark matter evolves with a nearly constant temperature during cannibalization. And so really the statement is that T prime scales like log T during cannibalization. And so in effect, these 3-2 self-annihilations are heating up the dark sector and causing it to evolve with nearly constant temperature and likewise nearly constant density, co-moving density. And so a way of saying this is during cannibalization, as the universe expands, a thermally secluded dark sector with a number changing process like this will cannibalize itself to keep warm. And now we can kind of explicitly see how this leads to the Elder scenario just by directly calculating the relic density of the dark matter. It's given by this equation, and in particular, it scales exponentially with the inverse dark sector temperature at freezeout, TF prime. And because freezeout occurs at the end of a period of cannibalization, during which the dark sector temperature is mostly fixed by the kinetic decoupling temperature, this means the relic density is exponentially sensitive to the kinetic decoupling temperature and has only subleading logarithmic dependence on the standard model temperature during cannibalization. And so this leads to the scenario in which the relic density is exponentially sensitive to the elastic decoupling process and has only subleading dependence on the processes that occur after kinetic decoupling during cannibalization. And so this is this Elder elastically decoupling relic scenario. And this is also a natural way to give light sub GeV dark matter. And so there's something I want to say. There's just kind of a quick lesson I want to pull from the SIMP and Elder scenarios, which is just to say that we see in moving from SIMP to Elder that by relaxing this assumption of thermal equilibrium between the two sectors during the dark matter freezeout, in the case of Elder, you realize a novel freeze-out mechanism for the dark matter, which can naturally give rise to light sub GeV dark matter. And so it's this lesson of relaxing thermal equilibrium that I want to think about later in the talk in the context of vector portal dark matter. Right. And so this vector portal dark matter model I'm thinking about is this dark photon model, which I'll now describe. And it's in the context of this model that I'll present new freeze-out mechanisms. So this dark photon model we're thinking about is a Dirac fermion dark matter particle chi, charged under a hidden U1 gauge symmetry with dark sector coupling alpha D, and with a mass with a dark gauge boson A prime that has a mass MA prime.
Sorry, I have a small question.
Yeah.
So this may go back to Amit's question. So for this, the relic abundance in this scenario is set by a 3-2 process because it's a strongly interacting, dark sector, or strongly interacting theory and you want it to be model independent. So you do this 3-2 process that sets your relic abundance.
Yeah. So you're thinking about the SIMP scenario. Right.
I guess I'm just wondering if you're considering. I guess, are you saying that it's strongly interacting mostly in the dark sector?
Yeah,
and
this is
not between the strong interaction is not between the dark sector and the standard model sector, right?
No, right. This is
okay. I see. Okay.
Yeah.
Sorry.
No. Yeah. Thanks for the question.
Right. If you don't mind, just a clarification. I mean, just a little. Is the cannibalism scenario in the SIMP model not possible because the dark matter is strongly interacting, so it freezes out, the dark sector freezes out, dark sector self-interaction freezes out before the dark sector standard model, whereas it's the opposite in Elder. Is that the idea?
That is the idea. I don't think it's a function of the dark sector coupling. I think it's more a function of the strength of the parameter that determines the thermal coupling between the two sectors, the elastic coupling.
Yeah.
It's also true in Elder that the 3-to-2's process is a strongly interacting process. But it's I guess the way I think about it is the order of decoupling of events. So the way I think about it is like in SIMP, the order of decoupling is the 3-to-2 freezes out first, and then the elastic scatterings decouple at some point. But so the 3-to-2 freezes out, the dark matter freezes out, and then later elastic scatterings decouple. So throughout the freeze out of the dark matter in the SIMP scenario, the two sectors remain thermally coupled, and then in Elder you basically just reverse the order.
Yeah.
So
Okay, that makes sense.
yeah.
Thanks.
Yeah. Thanks for those clarifications. So scroll back. Right. So this dark photon model. Right. So I was saying that so we have a dark photon A prime, and this dark photon A prime provides a portal to the standard model through the kinetic mixing with the standard model photon. Through this, like through this term outlined in blue here, which is controlled by the strength of this kinetic mixing parameter epsilon. So when this is written in the mass basis, like in the equation on top, the kinetic mixing between the dark photon and the standard model photon provides a coupling between the dark photon A prime and the standard model electromagnetic current, controlled by the strength of this kinetic mixing parameter epsilon. And so the kinetic mixing generates these interactions between dark matter particles and standard model particles. So we have elastic scattering between dark matter chi and standard model fermions. We have annihilations of chi's to the standard model, and we have decays of the A prime to the standard model, all of which are controlled by the strength of this kinetic mixing parameter epsilon. And I also want to restrict to the region of this dark photon model in which the dark photon is more massive than the chi, but not so massive, it's less than twice the chi mass. And so in particular, this restricts, this prevents decays of A prime to chi bar. And so this kind of focuses us in on the region of this model in which the two dominant dark sector number changing processes are this 2-to-2 process of chi's annihilating into A primes, and this 3-to-2 process of chi bar chi going into chi A prime. And so before moving on, I just want to think about the regions that we're leaving out of this model by making the choice of mass range that we do, and kind of why we leave them out. So in the region that we're leaving out, where the chi is heavier than the A prime, the dominant process controlling the thermal freeze out of the dark matter is the chi annihilations to A primes, this 2-to-2 process, which then promptly decay to standard model particles. And this injects energy into the standard model plasma and causes ionizations and heating, to which the CMB measurements are sensitive, and runs into deadly constraints for light dark matter. So for this parameters region of the model, this is rolled out by CMB constraints for dark matter less than around a GeV in mass. And in the opposite region of the parameter space that we're leaving out, where the A prime is heavier than twice the chi mass, this just reduces to the WIMP case, because now the 2-to-2 annihilations of chi's to A primes receives a huge kinematic suppression. It's no longer important. This 3-to-2 process of chi bar chi going into chi A prime reduces to a scattering process among the chi's, since the A primes decay promptly to chi's, to chi bar. And the dominant process controlling the freeze out of the dark matter is the chi annihilations to standard model, and which likewise runs into deadly CMB constraints for light dark matter in this model. And so now let's think about the two most important processes in the kind of mass region of this model that we're interested in. This 2-to-2 and 3-to-2 processes. So, and starting with this 2-to-2 process here at the left. So this 2-to-2 process receives a kinematic suppression from chi's annihilating into heavier A primes. But nevertheless, it can proceed at finite temperature, and in this part of the mass range can dominate in setting the relic density of the dark matter. And the scenario in which it's this process which determines the relic density of the dark matter has been previously studied in the so-called forbidden dark matter scenario. And what's found is that when it's this process determining the relic density receives an exponential enhancement factor by this same kinematic factor, which when you match to the observed relic abundance naturally leads to dark matter that's exponentially lighter than the weak scale. So this naturally leads to sub-GeV dark matter. And now let's think about this 3-to-2 process here at the right. So in the upper half of the mass range that we're considering, where the mass of the A prime is greater than 3/2 the chi mass, the then large kinematic suppression of the 2-to-2 process can be compensated for by this 3-to-2 process, which can actually then dominate in determining the relic density of the dark matter. And so when it's this 3-to-2 process that determines the relic abundance, this has been previously studied and referred to as not forbidden dark matter. And this is also a natural way to give rise to light sub-GeV dark matter. But now in both the forbidden and not forbidden dark matter scenarios, the explicit assumption is made in which the two sectors remain thermally coupled throughout the freeze-out process. And so now I want to borrow this lesson that I mentioned in the case of SIMP and Elder, and relax this assumption of thermal equilibrium and see what happens. So what I want to do is consider cases where this kinetic mixing parameter epsilon is small but non-zero, such that the dark and standard model sectors are allowed to kinetically decouple, through any of these processes that couple the two sectors during the freeze-out process of the dark matter. And so during which the dark sector evolves with its own separate temperature T prime, which is different from the standard model temperature in general. And in doing so, we'll find a rich set of new pathways to the relic abundance of dark matter in this model. And so this is really the kind of first fully careful treatment of the full range, kind of region of parameter space of this model, including the region where one needs to relax the assumption of thermal equilibrium during thermal freeze-out. And among these new pathways, I want to highlight in a bit of detail this kinetically decoupling relic scenario. So now let's think about this Kinder scenario, this kinetically decoupling relic. So I want to think about Kinder by first examining the thermal history of a specific realization of Kinder. And so this is a bit of a dense slide, but this will provide just a summary of kind of the slides to come. So I'll just state the events that happen in this thermal history of Kinder. So let's think about a specific realization of Kinder where the thermal coupling of the two sectors is controlled by the A prime to standard model decays. And let's also consider the case that among the two dark matter number changing processes, the dominant process is the 3-to-2 process. So it's the 3-to-2 process that freezes out after the 2-to-2 process. And so this is in this not forbidden region of the parameter space where the mass of A prime is greater than 3/2 the chi mass, and it's the 3-to-2 process that dominates. And so the thermal history of Kinder will proceed through 3 distinct events. So the first event will be the kinetic decoupling of the two sectors, which happens when the A prime to standard model decays no longer efficiently keep the two sectors thermally coupled. And when this happens, the dark sector evolves with its own separate temperature T prime, different from the standard model temperature, and the two sectors are thermally secluded. And this happens while the 3-to-2 and 2-to-2 processes are still active and still maintaining chemical equilibrium in the dark sector and at zero chemical potential. And so we'll see that after kinetic decoupling, this leads to the onset of a cannibalization process in the dark sector. And the second event that occurs in the thermal history of Kinder will be the freeze out of the 2-2 process. And this happens while the 3-2 process is still active. We'll see that this leads to a period in which the dark sector evolves with a non-zero chemical potential. And we'll also see that nevertheless, cannibalization proceeds after the freeze out of 2-2, even in the face of this non-zero chemical potential. And this constitutes an extension of the usual cannibalization scenario. And then the last event to occur in this thermal history will be the freeze out of the 3-2 process. And this signals the freeze out of the dark matter. But because cannibalization occurs from the time of kinetic decoupling through 2-2 freeze out and up until 3-2 freeze out, this leads to a scenario in which the relic density is set by the kinetic decoupling process. In this case, by the decoupling of the A prime to standard model decays. So this is a dense slide, but I'll unfold each of these events one by one in the slides to come. So let's jump into this thermal history. And let's look at the thermal history for a specific case in which the mass of the A prime is 1.8 times the chi mass. So now I'm defining this parameter R, which is defined to be MA prime divided by M chi. And so this is in this not forbidden region of the parameter space where the 3-2 process dominates the 2-2. And let's also examine the case in which this is also for the case in which the dark matter mass M chi is 10 MeV, so for light dark matter. And in the top panel here, I'm showing the abundance of the dark matter Y chi plotted as a blue line, plotted as a function of this quantity X, which is defined as the dark matter mass M chi divided by the standard model temperature. And so as the universe expands and cools, this quantity X increases. And in the bottom panel, I'm plotting the dark sector temperature T prime, plotted as a blue line, also plotted as a function of this quantity X. And for comparison, I'm showing the standard model temperature T, plotted as a red dashed line. And so at early times in this thermal history, all these processes shown at the right here are active, proceeding at rates greater than Hubble. The A prime to standard model decays maintain thermal equilibrium between the dark and standard model sectors, and the combination of 2-2 and 3-2 number changing processes maintain chemical equilibrium in the dark sector. And so at early times, things are in thermal and chemical equilibrium. The dark sectors, the dark and standard model sector evolve with equal temperatures, and the abundance of the dark matter, chi, depletes according to its equilibrium distribution, which is shown as a green dashed line in this top panel. And so this early time behavior is kind of what I'm calling thermodynamic phase A in these thermal history plots. And so this continues up until the first event of Kinder, which is the kinetic decoupling process. And that's indicated by a pink vertical dotted line in these thermal history plots. And kinetic decoupling happens when the rate at which these A prime to standard model decays transfer energy between the two sectors is no longer efficient enough to keep the two sectors thermally coupled. And you can see that after kinetic decoupling, the dark sector temperature T prime deviates from the standard model temperature. And likewise, the dark matter abundance deviates from its equilibrium distribution. And you can also see that after kinetic decoupling, the dark sector temperature evolves very slowly compared to the standard model temperature. And likewise, the dark matter abundance evolves very slowly compared to its equilibrium distribution. And that's because kinetic decoupling happens while these 2-2 and 3-2 number changing processes are together maintaining chemical equilibrium in the dark sector and net converting mass to kinetic energy in the dark sector, which is now thermally secluded. So they're heating it up in a process of cannibalization, like the one we saw in the context of Elder. So now let's look at this cannibalization scenario again in the context of Kinder here. So again, cannibalization occurs after kinetic decoupling. And after kinetic decoupling, the two sectors are thermally secluded. And so the dark sector, they evolve with constant co-moving entropy density. And at the same time, the 3-2 and 2-2 number changing processes are still active, proceeding at rates greater than Hubble, and maintain chemical equilibrium in the dark sector at zero chemical potential. And both of these facts can be used to determine the relation between the dark sector temperature T prime and the standard model temperature T. We find that T prime scales logarithmically with the standard model temperature T, and again is mostly fixed by its value at kinetic decoupling TD. And so again, during cannibalization, T prime scales like log C. And so this first phase of cannibalization that occurs in the Kinder scenario is the conventional case that has been previously studied and occurs in the context of Elder as well. And then the second event to occur in the thermal history of Kinder is the freeze out of this 2 to 2 process, which occurs after the 2 to 2 process falls below the rate, after its rate falls below the Hubble expansion rate. And so when this happens, it falls out of equilibrium and no longer maintains detailed balance between its forward and reverse processes. And at the same time, this occurs while the 3 to 2 process is still active, proceeding at a rate greater than Hubble, and does maintain detailed balance between its forward and reverse processes as it's in equilibrium. And so now you have one detailed balance relation among two dark sector chemical species. And so during this time after 2 to 2 freeze out, the dark sector begins to evolve with a non-zero chemical potential set by this 3 to 2 process. But nevertheless, even in the face of a non-zero chemical potential, cannibalization of the dark sector continues, with T prime continuing to scale logarithmically with the standard model temperature T. And so this is an extension of the usual cannibalization scenario, which proceeds during this period where the dark sector evolves with a non-zero chemical potential, and is supported solely by this 3 to 2 process, which is now among two chemical species of dark sector particles. And so this continued cannibalization in this Kinder scenario is important because returning to these thermal history plots, when finally the 3 to 2 process freezes out, and I'm indicating this by a purple vertical dotted line in these thermal history plots, and this signals the freeze out of the dark matter, because the dark sector has been cannibalizing from the time of kinetic decoupling, during which the dark sector temperature evolves logarithmically with the standard model temperature, and likewise during which the abundance of the dark matter evolves, roughly constant. This leads to the scenario in which the dark matter abundance at thermal freeze out is mostly fixed by its value at kinetic decoupling. And so here we see, in these numerical solutions, this Kinder scenario. And we can also just see this by explicitly calculating the relic density. Again, the relic density is given by this equation, and in particular it scales exponentially with the inverse dark sector temperature at freeze out TF prime, as this purple arrow is pointing to. But again, because cannibalization occurs from the time of kinetic decoupling through 2 to 2 freeze out and up until the freeze out of the dark matter, during which the dark sector temperature evolves logarithmically with the standard model temperature and is mostly fixed by its value at kinetic decoupling TD, this leads to the scenario in which the relic density is exponentially sensitive to the kinetic decoupling temperature and has only subleading logarithmic dependence on the standard model temperature during the cannibalization process. And so this is, so here we see explicitly this kinetically decoupling relic or Kinder scenario happening in the context of this dark photon model.
Sorry if you don't mind me asking. This was mainly because maybe I wasn't following with enough attention. But why does cannibalization only occur after decoupling?
Well, yeah, you need, you need the two sectors to be you need the dark sector to be thermally secluded in order to in order to have this process of mass to kinetic energy conversion be how do I say it, if the two sectors are thermally coupled, then basically the thermalization of the two sectors just like the dark sector just couples to the standard model and really kind of, together that system is just dominated by standard model degrees of freedom.
Okay, yeah, makes sense.
Yeah. Okay, so now that we've seen the thermal history of a specific realization of Kinder, let's look at the generic regime of the parameter space of this dark photon model in which Kinder occurs. So here what I'm showing is generated from data over many solutions like the one whose thermal history we just examined. And what I'm plotting, like each of these lines, are lines of constant relic density of the dark matter set to the observed value, where each contour line is also for a fixed dark matter mass m chi. So that's a really packed sentence. So I'm gonna say it again. So each of these contour lines is a fixed contour line of the dark matter relic density fixed to the observed value. And each individual contour line also represents a fixed dark matter mass m chi. And so the dark matter masses run from 1 MeV to 1 GeV, going from lowest to highest epsilon in log steps. And it's also, and so I'm plotting this in the space of kinetic mixing parameter epsilon versus dark sector coupling alpha. And so in light of the thermal history we just examined, we can think of the y-axis. Epsilon is parameterizing the strength of the process, controlling the thermal coupling of the two sectors. And we can think of the x-axis, alpha d, as parameterizing the strength of the process, of the dark matter number changing process. So for most of the, for this part of the parameter space where r is 1.8, we can think of the x-axis as parameterizing the strength of this 3-to-2 process. And the solution whose thermal history we just examined sits where this pink star sits in the plot. And that pink star sits right here in this Kinder region, where you can see that lines of constant relic density, they turn horizontally along the x-axis. So they flow independently of the dark sector coupling alpha, and they stack up along the y-axis. So they stack up along the kinetic mixing parameter epsilon. And so this is precisely this region where the relic density of the dark matter is determined by the kinetic decoupling process, which is controlled by epsilon, which for most of this parameter region is dominated by the A prime standard model decays, like in the thermal history we examined. So we can see that this Kinder, this Kinder region here, and we can see that it's a generic region in this parameter space. I should say kind of briefly that we shouldn't, I kind of plotted this out to pretty large alpha values, but we really shouldn't trust any, much from alpha greater than like 1 or 4 pi or something onwards, because there's no, we didn't calculate loop corrections or anything like that. So but yeah, we can see that Kinder is a generic region, or I want to call it a regime. Yeah, we can see that Kinder is a generic regime in this dark photon model. And we can also see where it lies in relation to other distinct regimes which represent freeze-out mechanisms in this dark photon model. So as lines of constant relic density flow up to higher values of epsilon, you start to enter the region where the two sectors do remain thermally coupled, where epsilon is large enough so that the two sectors do remain thermally coupled through the freeze-out process. And then you enter the not forbidden dark matter regime, the NFDM regime. And so here you see lines of constant relic density flow vertically along the y-axis, so independently of the strength of the process controlling the kinetic coupling of the two sectors, and stack up along the x-axis. So they're fixed by the strength of the 3-to-2 process. And so this is precisely this region of the parameter space that was previously studied, where the two sectors remain thermally coupled, and the relic density is determined by the 3-to-2 process. And so that's this NFDM region or regime. And going to still higher values of epsilon, you can see where the WIMP, the conventional WIMP regime lies. At some point you get to high enough values of epsilon where the dominant process determining the relic density is the chi annihilations to standard model. And because the strength of that process is controlled by the combination of parameters epsilon squared times alpha, here lines of constant relic density trace lines of constant epsilon squared times alpha. And so so this is pretty cool, because you can see that Kinder's generic regime in this dark photon model, and you can see where it lies in relation to these other previously studied regimes.
So can I ask a semi-naive question about the relationship between this and Elder? So I think I can see that because you're exponentially sensitive to the decoupling temperature, these fixed relic density lines end up, being roughly flat with respect to epsilon in the Kinder region.
Right.
But then the major difference from Elders is that your 3-to-2 process in this case is allowed for by sort of a not forbidden condition rather than like a strong coupling condition, and maybe something different with respect to how chemical equilibrium ends up playing out, because it's not a 3-to-2 process with the same species. Did I?
Right.
Okay.
Yeah, exactly. That's more or less exactly how I would summarize it. I guess, like you said, you have, I guess there's two I guess there's also one other distinct difference, which is it's actually not trivial to the way it works, that you can realize a scenario where the kinetic decoupling is controlled by, say, the A prime to standard model decays rather than elastic scattering that's actually not so trivial, because actually the A prime to standard model decays can transfer a significantly greater amount of entropy between the two sectors after kinetic decoupling. And so there's they redshift away a lot more slowly than the elastic scattering process. And so there's like a lot of things, like I'm simplifying a lot here by, like, making assumptions of conserved co-moving entropy density after kinetic decoupling and things like that. And like in our paper, we kind of have a more full treatment where we really more realistically are able to get analytic results from, but even more realistically considering like non-zero entropy transfer. But yeah, so that was kind of, I didn't mean to complicate things, but I guess the only
no, yeah, I see, that's important too. It's not just a scattering process that's falling out. It's something that's actually dumping.
Yeah, exactly.
Into the,
yeah, exactly. So I guess I would say those are the two, like, kind of extensions from Elder. It's like you have there's a different reason why the number changing process, why the 3-to-2 process can play an important role. Now the evolution of the dark sector is less trivial because this 3-to-2 process is among two chemical species, and also this third ingredient of, like, it's not trivial that it works. Like it's maybe even surprising that it works out that you can realize the same kind of behavior even when the kinetic decoupling is controlled by a different process than elastic scattering.
Great. Yeah. Thanks.
Yeah. Thanks. Okay, so right, so far I've focused the discussion around this Kinder mechanism and in particular this region of the parameter space where R is greater than 1.5. So I was showing representative results for R 1.8. But so in this region where R is greater than 1.5, again where R is where MA prime is greater than 1.5 times M chi, the 3-to-2 process freezes out last and dominates over the 2-to-2 process during the freeze-out. During thermal freeze-out, and so I'm repeating these results here in the left-hand panel, but in the right-hand panel I'm also showing the same results, except for the only difference here is that this is for R 1.4, and so I'm using this as a representative example of like the region of the parameter space where R is less than 1.5, and in this region, like, the ordering of the freeze-out of the number changing process is reversed. So the 2-to-2 freezes out last. So the 2-to-2 process dominates over the 3-to-2 in this region. So this is this so-called, like, this is the kind of the forbidden kind of region of the parameter space, the forbidden dark matter region. And in this region, you can see that there's 4 distinct freeze-out regimes. At high enough epsilon, there's also like a WIMP regime it's kind of at higher epsilon than I've plotted here, but yeah, in this range, there's 4 distinct freeze-out regimes, which I've labeled 1 through 4, and among these regimes, the only one that has been previously studied is this regime 1. So this regime 1 represents the previously studied forbidden dark matter scenario, where the two sectors remain thermally coupled throughout the freeze-out process, and the relic density of the dark matter is determined by the 2-to-2 process. So that's regime 1. But you can see that below, even like already at like epsilon around 10 to the minus 5, by relaxing thermal equilibrium, you realize three new distinct freeze-out regimes which represent kind of novel freeze-out mechanisms. These regimes 2 through 4 are new freeze-out regimes, and I won't go into these regimes in detail. It's just kind of a lot, but yeah, I guess I will say that kind of regime 4 represents a kind of another realization of Kinder-like behavior. And I guess like the main point I want to take from this slide is just kind of backing up and looking at, really, I guess, laid out like the kind of full parameter region in this mass range of the dark photon model, and seeing all the all the freeze-out regimes that can arise in this model. 4 of which we find are new simply by relaxing this assumption of thermal equilibrium. And so yeah, this like relaxing thermal equilibrium kind of reveals this rich set of new freeze-out histories in this dark photon model, which was, which I guess to me I found surprising, because this is already a very well studied hidden sector model. And so I think there's a cool lesson to pull from this, which is, as we kind of expand our thinking into the kinds of models that can exist at these unexplored regions of the parameter space that haven't been explored experimentally, and we're kind of thinking about the models that might exist at these new scales, like for example to naturally produce light, like at light dark matter scales. I think it's important even to really carefully study, even well understood hidden sector models, and in particular, carefully think about the kinds of non-trivial thermal evolution that could take place in these models to really mine the full possibility of novel freeze-out mechanisms that might exist in these models. And so now that I've so now that we've really seen like kind of full set of regimes which representing not distinct freeze-out histories in this vector portal dark matter model and in this dark photon model. Like now that we've really fully explored this parameter space, let's examine the experimental constraints on all of these regimes, and really kind of update all the constraints that had been placed on vector portal dark matter in the past without considering this region, without relaxing the assumption of thermal equilibrium. And so what I'm showing here is the data, is the constraints plotted against the data, which is matched to the observed relic abundance of the dark matter in this model. And in the left-hand panel, again, I'm showing results for R1.8. And in the right-hand panel, again, I'm showing results for R1.4. And this is plotted in the space of kinetic mixing parameter epsilon versus the dark matter mass. And all the distinct freeze-out regimes that we identified in the previous plots are labeled in blue here, and divided by these blue kind of dashed dot lines. And so for R1.8 we have WIMP, NFDM, and Kinder regimes, of which the Kinder regime is new, and for R1.4 we have regimes 1 through 4, of which only the one that has been previously studied is regime 1, the forbidden kind of dark matter scenario. And the constraints I'm plotting here in light blue are direct detection constraints. The constraints shown in purple are constraints from supernova cooling that like particle production and escape implies in this model. The constraints shown in red are constraints on the self-interaction cross section, and this constraints shown in green are CMB constraints on KINetically into the standard model, and the constraints in light gray are like beam dump and accelerated constraints, and this kind of dark gray region shows where the model is kind of very non-perturbative. So greater than, in this dark gray region is where alpha is greater than 4 pi. And so we just kind of saw this Kinder mechanism. So let's first look at this region where we see that there's this kind of tiny available window for Kinder, but in general the kind of main takeaway here is that Kinder in this realization runs into large self-interaction rates and a large S-wave annihilation signal in the CMB. And there's also kind of an update here, which is that by more carefully examining the thermal history that takes place in this model, we find that the NFDM region, which previously had an available window, is entirely rolled out. And it's sort of like the available window that existed in the NFDM region kind of gets transferred to this Kinder region. And so that's, so that runs into pretty strong constraints, Kinder. But among these new freeze-out mechanisms that we find, the two that kind of provide the most viable available windows for future experiments searching for light dark matter are these regimes 2 and 3, shown in the right hand panel. Okay, and so yeah, so I want to, you know, so we kind of went through this whole Kinder story, and then we saw that you know, the in fact the available experimental window for it is quite small. So I want to you know, not, you know, I want to make sure that we're still excited about Kinder, and maybe just briefly describe a way that we can relax these CMB and self interaction constraints, and preserve it on this Kinder scenario. And so this is kind of, this is like just going to be a really brief statement about work that we're doing now that we should we should report on soon. But so, like, imagine modifying the model, the dark photon model I just described, to consider the case in which the dark matter is a pseudo-Dirac fermion charged under the hidden U1, and at low energies, the hidden U1, where the hidden U1 is broken, the dark matter splits into these two non-degenerate Majorana fermions, Chi1 and Chi2. And so long as you make this modification such that the mass splitting between Chi1 and Chi2 is smaller than the smallest freezeout, dark sector freezeout temperature you consider in this model, then you can make this modification without modifying essentially any of the early time cosmology throughout freezeout that I just described. So this whole Kinder story and everything. You can make this modification without modifying those things, essentially. And but this modifies the late time physics in a way that's beneficial for relaxing these constraints, because now the vector coupling between A prime and Chi's is off diagonal, as these Majorana fermions can't carry conserved charge, and so this means that any process you could write, the leading order processes that you can write down, which contribute to the self interactions and to the CMB constraints, occur at leading order at one loop. So for example, here's the self interaction process among Chi1s, which occurs at leading order at one loop, and likewise the Chi annihilations to standard model. And so, I mean, for example, you could also write down processes that had like Chi1, Chi2 scattering into Chi1, Chi2, or Chi1, Chi2 annihilating into the standard model. But those those, you know, similarly run into strong Boltzmann suppression at late times. And so this is a way that you can, you know, this is a modification you can make to this model that, like I said, leaves the early time cosmology, all the cosmology we just described, like unchanged, and but which can relax these CMB and self interaction constraints and open up a lot more parameter space for Kinder.
Just a quick question, sorry, if you don't mind.
Yeah.
Since the self interaction are there or loop induced, like, wouldn't you need stronger couplers for them to be efficient?
Well, I'm maybe not appreciating what you're asking, but I think I guess what I'm trying to say is that's kind of like that's the idea. It's not the self interactions that are important for the early time cosmology, like the you know, so long as the mass splitting is sufficiently smaller than the freeze-out temperatures you consider, then all the kind of the important processes that you know we've thought about, like, I mean, the important, like these 3 to 2, 2 to 2 number changing processes, as well as the processes controlling kinetic decoupling, those are like that cosmology is unchanged. I don't know if I'm explaining this well. It might not. Yeah, sorry. Maybe I feel like I'm not quite answering your question. So maybe you could. Yeah, could you repeat it or maybe elaborate it a bit?
Yeah. So what I was thinking, like the 3. Okay, maybe that's my confusion, because I thought the 3 to 2 was a form of self interaction that was cannibalizing the dark matter.
Oh, I see.
I think I misunderstood. I thought the self interaction diagram that you saw here, I thought the cannibalism in this way was happening through loop induced processes, but then that's what I was wondering, like, then wouldn't it be suppressed quite a bit? But I think I'm misunderstanding.
Let me think about the diagram. I have to remind myself of the diagram, actually. This wouldn't be nice to have a chalkboard, but
I think you answered, Patrick, though, because it's a temperature dependent statement. Yeah.
Yeah, I mean, yeah, that's definitely true as well. Yeah,
I think even though it's a temperature dependent statement, what this is the delta less than TF is telling you is that if your Chi2 is long lived enough, then the 3 to 2 process can be important. But I think what Ahmed is saying is here is that for the self-interaction process, why can't I consider Chi1, Chi1, Chi1 going to Chi1, Chi1 through this Chi2 loop?
Oh,
Right?
yeah.
But then that would be suppressed, right?
Yeah, I guess that process would be loop suppressed, but you would have, I mean, you would have, I guess here the important processes like are among Chi1s and Chi2s, which.
No, it's also silly me. I misunderstood. I thought the self-interaction diagrams that you were mentioning here were in place of the 3 to 2. My bad.
Oh no, yeah,
that was my
this self-interaction is meant to just be contributing to the self-interaction constraints, but this isn't the not to be confused with like the 2 to 2 and 3 to 2 processes that control the thermal freeze-out.
Yeah.
Then are important in the thermal freeze-out.
So yeah, that was my misunderstanding.
So just because we're at, we have about minus 10 minutes on the clock, do you want to wrap up and then we can continue a discussion afterwards once people who need to leave have had a chance to.
Yeah, I'll wrap up now. So so basically we've fully characterized the thermal freeze-out histories of this dark photon model, including the region of the parameter space where we relax this assumption of thermal equilibrium during thermal freeze-out. In doing so, we found a rich set of novel pathways to the relic abundance, which naturally produce light-dark matter. And among these, I highlighted in a bit of detail this kinetically decoupling relic, where the relic abundance is set by kinetic decoupling of the dark and center model sectors, which kind of generalizes previously studied cases of this kind of behavior, like the elder scenario. And among this rich set of novel pathways, we found that some of them provide new viable target regions for future experiments searching for light dark matter. Yeah, thank you. Thanks, everyone.
I'll clap on behalf of everyone. So yeah, thanks for a really nice talk. As I said, I can stick around, and those who want to stick around to ask a few more questions are welcome to do so. We've already had quite a few questions, but you can either just jump in or raise your hand in the chat if you have any questions for Patrick.
Well, thank you for the very nice talk, Patrick.
Thanks, everyone.
Thanks.
So I have a question regarding that last part with the Inelastic.
Okay.
Characterize. So this delta function says to me that if the mass splitting is small enough, then basically I have almost kind of a WIMP-like scenario. Even though I still have inelastic, my Chi2 particle is kind of long-lived, right? That I could have some sort of a co-annihilation happening. So so what is the relative strength of the co-annihilation compared to the 3 to 2 scattering? I'm still not 100% sure about the 3 to 2 scattering in this case. Maybe that's why I'm asking a question. Because
so I think in this case, the 3 to 2, I guess I'm a bit confused about what you mean by the co-annihilation. It's like, I guess this would be like Chi1, Chi2 going into standard model through the, this would be Chi1, Chi2 going into standard model through through the S channel.
Through the S channel, yeah.
I see.
Because if I'm looking at the strong coupling in the dark sector, then I could have a 3 to 2 with involving all Chi1s through this loop diagram. But I think the most dominant would be the co-annihilation process.
Well,
or maybe I'm wrong.
I think it's so I think it's so for example, if I compare it to like the Kinder scenario that we were looking at, like I guess like the question is whether how this compares to the 3 to 2 process, which is like I guess it's like Chi1, Chi2, it would be like Chi1, Chi2, and like either a Chi1 or Chi2 in the initial state. I guess the dominant one being the lighter of the two, and going into like Yeah, so maybe like chi1, chi2, chi1 going into like chi2 a prime. So I think as long as the mass splitting is small enough that there's no significant Boltzmann suppression at those early times, then the reason the co-annihilation is subdominant to that 3-2 process is the same reason it's subdominant like in just the basic case that we studied, which is just the smallness of the kinetic mixing parameter. Yeah, I mean it's kind of a combination of it's kind of a combination of those two parameters, epsilon and alpha. But like the suppression, I think in the co-annihilation comes from it's controlled by the smallness of the kinetic mixing.
Maybe I was misunderstanding it in my head then, because like the reason you could have the 3-2 but not the 2-2 is that or 2 to whatever is that the 2 to whatever didn't satisfy sort of the special kinematic conditions that you're winning in the very high energy tail of your distribution and getting sort of that forbidden, like I'll call it, enhancement, whereas in the 3-2 process that is kinematically allowed. Was that the reason that the 3-2 was allowed and the 2-2 wasn't allowed? Or
yeah, I think I'm probably just being confusing because maybe I used 2-2 to say like to identify two distinct processes. So I think we have to make sorry. I was just talking about like comparing the 2-2 annihilations to the standard model of the 3-2 process, but it's indeed the case that that is the mechanism of why the 3-2 dominates over the 2-2 like among the dark sector number changing processes. It's the 3-2, which is usually subdominant because it has an extra like Boltzmann factor and suppression factor in the initial state, but it can dominate over the 2-2 process in this regime that I described in the model because of the kinematic suppression of the 2-2 process. Sorry, am I explaining?
No. I see what you mean. Yeah, but then relatively speaking, why is this 2-2 process shutting off when in the standard model it's not? Well, yeah, that's just because epsilon's small.
Yeah, exactly.
So I see the point of the smallness of the epsilon. So, but then if I take this diagram, the self-interaction diagram, and I tack on a chi1 vertex in the middle of the incoming chi1s, so that gives me the 3-2 process that we're talking about here, right? So this process is still loop suppressed though. So are you saying that the loop suppression is smaller than the the loop suppression is less dominant than the smallness of the epsilon, because here now I have an alpha to the power 5. Is it alpha down to the power 5 cross section?
So even in the inelastic case, I don't think the 3-2 proceeds through a loop suppressed process. There are two vertices. There's two factors of. Yeah, actually, maybe I should just scan up to one of these 3-2 diagrams.
I'm looking at the wrong diagram, I guess.
So I guess let's. Well, no, maybe. That's a good slide to look at. Let's just look at. Yeah, like this slide, I guess. So if this was the inelastic case, I guess, you would have this same diagram, right? I guess, but you would have like chi1, chi2, chi1, say, going into like, and this is the same A prime vertex going into like a chi2, and then you'd end up with a chi1. So, I mean, you would have the same, do you see what I mean? Like you would have the same, like the topology of the diagram would be the same. It would just be like, you would exchange some of the chi bars for chi1s or chi2s, like, but yeah, like, because this, as I've said, because this is like a temperature dependent process, and when you consider the case of the kinetic, like when at early times the mass splitting is small enough like that, I mean, it leaves the cosmology unaffected, and the reason this process